Hello students, in this video we are going to discuss about the extrinsic semiconductors. Extrinsic semiconductors means where the impurities are added to a pure semiconductor, they are called the extrinsic semiconductors. So basing on the type of the impurities added, these are again classified into N-type semiconductor and P-type semiconductor. In an N-type semiconductor, we'll be adding the pentavalent impurities to a pure semiconductor. We know that pure semiconductors are examples, we are taking silicon and germanium. So for this silicon and germanium, if we are adding the pentavalent impurities, it forms N-type semiconductor. And if we are adding the trivalent impurities, it forms P-type semiconductor. Let us see the formation of this N-type and P-type semiconductor in detail. So in N-type semiconductor, there will the impurities are the pentavalent impurities. Pentavalent impurities means they will be having the 5 valence electrons. So in periodic table, 5A group elements are used for this doping. Examples like phosphorus, arsenic, antimony, the other name for antimony is TBM, and bismuth. If these type of impurities are added in doping with the pure silicon atom or the germanium atom, then it is called N-type material. Whereas in P-type material, trivalent impurities are added. Trivalent impurities means those are having the 3 valence electrons. In periodic table, mostly the 3A group elements, these are used in doping to form the P-type material. So the examples for these trivalent impurities are aluminium, gallium, boron, indium, etc. So what happens inside the pure semiconducting material when these impurities are added? N-type semiconducting material. In N-type semiconducting material, already we discussed pentavalent impurities are added. These are added to our pure semiconductor. So our pure semiconductor is having 4 valence electrons. Already these are forming 4 covalent bonds with other 4 semiconducting materials. So as here we are using pentavalent impurities, these are having 5 valence electrons. So as one is remaining extra, so this one extra electron is free to conduct the electron, and this is the conduction electron, and it can easily move away from the impurity atom. So the conduction electrons here will be going to the conduction band, and this electron is from the impurity atom. So the impurities are releasing the electron. That's why these are called donor atoms. So in N-type semiconductor, the impurities are called donor atoms or simply donors. The majority charge carriers in these N-type semiconductor are electrons, and minority charge carriers are holes. So this is the structure formed when a pentavalent impurity is doped for a pure silicon atom. So this is the impurity we have taken. Here we have taken the TBM, and this is containing 5 valence electrons. Among these, 4 valence electrons are forming 4 covalent bonds with 4 silicon atoms. That is with the pure semiconducting material. And the 5th electron, this is the free electron to carry current. So these free electrons, they'll move to the conduction band. And so these electrons, here in this figure we can see clearly, these electrons are free to move and they'll carry current. As the electron is coming out from the atoms, that is the impure atoms, they are called the these are called the donor atoms, that hence they form the ions. So these are called the donor ions. After releasing the electron, they form the positive lattice sites. So these are called the donor ions and the electrons. And last we have seen the minority charge carriers or holes. Here the holes are there. These minority charge carriers are due to the intrinsic nature of this pure semiconductor. That is, pure semiconductors, as temperature increases, their covalent bonds will break and electrons from valence band, they'll move to the conduction band, leaving a hole in the valence band. So those holes will be present as minority charge carriers. So we can say Majority charge carriers electrons are from the impurity atoms, that they are called the donor atoms, and the minority charge carriers are due to the intrinsic nature of the semiconductor. Minority charge carriers are due to the intrinsic semiconducting nature. Majority charge carriers are because of the doping. This figure shows the energy level diagram in n-type semiconductor. So, we know that there is a valence energy level and a conduction energy level in semiconductors. Here, because of the impurity atoms, one more energy level is coming, that is the donor energy level. This donor energy level is represented with ED. This energy level lies near to the conduction energy level. So donor energy level lies near to the conduction energy level. So this figure shows as the electrons present in the valence band, these electrons are at different energy levels in valence band, and these valence electrons, they'll gain the energy and they move to the conduction band due to the intrinsic nature. And already because of the free electron present in these donor atoms, those electrons also present in the conduction band. So here we can see more number of electrons present in the conduction band and very less number of holes present in the valence band. So electrons are called the majority charge carriers and holes are called the minority charge carriers. Now let us see what are p-type semiconductors. In p-type semiconductors, the impurities are trivalent impurities. These are having 3 valence electrons. Already we know that our pure semiconductors contains 4 valence electrons. So as here our impurities are in deficient with 1 electron. So these are ready to accept 1 electron. These are ready to accept to this 1 electron. That's why these impurities are called acceptor atoms. So what happens? Our silicon will form 4 covalent bonds. Here only 3 valence electrons are there. So to form that 4th bond, the inner electron in the atom will be coming and forming that covalent bond, and a hole is created in that inner shells. So in forming the bond with the silicon, there are 4 covalent bonds, a hole is created in these impurity atoms, that is trivalent atoms. The majority charge carriers in this p-type semiconductor are holes. That's why the name it is given as p-type, because holes are having positive charge, so the name p-type. As electrons are having negative charge, the name n-type over there. And the minority charge carriers are electrons. These minority charge carriers are due to the intrinsic nature of the semiconductor, and majority charge carriers are due to the impurities, that is the acceptor atoms. Here in this figure we can clearly see the impurity atom. Here we have taken the boron, trivalent impurity. So forming 3 covalent bonds with 3 silicon atoms. And to form the 4th bond, it is in deficient of with 1 electron. So this deficient is like a hole. So this hole will are the particles that are existing in the impurity atoms. So more the impurities, the more the holes are. So these holes now will carry current in this p-type semiconductors. So as these are in deficient with 1 electron, the lattice sites are having the negative charge. These lattice sites are having the negative charge. So leaving hole in the valence band to carry current. These are free now. These holes are free. And due to the intrinsic nature, electron hole pairs are generated. The electron from the valence band, it moves to the conduction band, leaving a hole in the valence band. So these electrons in the conduction band are the minority charge carriers, and holes in the valence band are the majority charge carriers in this p-type semiconductor. This is the energy level diagram in p-type semiconductor. In p-type semiconductor, we are having the valence energy level and the conduction energy level, and due to the impurities, we are having one more energy level. These impurities are called acceptors, no? So that's why that impurity energy level is called the acceptor energy level, represented with EA. So this acceptor energy level lies near to the valence band. Lies near to the valence band. And here we can see trivalent impurities. They are in deficient with one electron. So the holes are formed in the valence band. And due to the intrinsic nature, some electrons will be going to the conduction level, leaving hole in the valence band. So as here the holes are in the majority number, that's why they are the majority charge carriers, and electrons are in very less number, they are called the minority charge carriers.